Welcome to IA 201 Motors and Controls. Today we are working on Chapter 11, Transformers. And I jumped ahead in the book. This is a jump ahead because transformers are so important in the entire electrical world that I wanted to bring them forward and talk about transformers. Number one, because of its conceptual importance. And number two, we are definitely going to be wiring up and need to understand control power transformers. And that's going to be something we do early on in our lab. So I wanted to make sure everybody understands the terminology and the technique for doing that wiring. You guys have already run into some challenges with wiring diagrams on some of the earlier chapter 1, chapter 2 stuff. So what I want to do was dive into that and really start to understand transformers. So we're off in chapter 11. Chapter 11 has a lot of good information, and this is really worth reading once or even twice if you didn't get it the first time. And it talks about transformers. It talks about one of the earliest and most interesting technology battles of our in the United States ever, and that was a giant battle between Thomas Edison and Nikola Tesla. And Edison is sort of credited with all sorts of magical powers when it comes to electrical things. And he is the big name that's well known. Edison was in a fight between Westinghouse to gain kind of the ownership, the mastership of the entire electrical distribution system in the United States. And Edison believed in DC, or direct current. And he fought with George Westinghouse, who purchased patents from Nikola Tesla. And I think it's interesting now that this battle, this great battle between the minds of Tesla and Edison, is now, Tesla doesn't even get a mention in the book about transformers. And it was Nikola Tesla's designs that made all of this possible, made our entire electrical system possible today. His basic designs for three-phase power generation, AC, and his designs for motors, and his concepts around transformers and power distribution. He's really the guy there. And here we are on our chapter 11 talking about his core invention, no mention. So here's a mention of Nikola Tesla. So transformers. They do what it's in the name. They transform power from one voltage to a different voltage. And why do you want to transform power from one voltage to another voltage? Well, the why in almost anything in the industrial world is money, to distribute large amounts of power at a reasonable cost. So how does that work? Well, if I jack up my voltage to 15,000 volts or 30,000 volts, and I send it over a wire, I tend to have less power loss, right, for my total volume of energy sent. So the total power sent, I tend to have less power loss than if I just try to distribute that power at a low voltage and high current. That's the key, current. If I have relatively low current, right, that low current allows me to use smaller wires, and that low current allows me to have less heat loss. Less current means less energy flying off that wire in terms of heat. So therefore, I want to reduce my current. So a transformer has two effects. It can increase or decrease voltage, and it can increase or decrease current. Generally speaking, we use step-up transformers to transmit power across long wires. That way we reduce our current and increase the voltage. And then we do a step-down transformer at your house or at your business to take that high voltage, at 15,000 or 30,000 volt wire, and convert that into something usable in your building. Why don't I want 30,000 volts in my building? Because it's crazy dangerous. That stuff can arc a couple of feet. You get near a piece of power equipment and you get shocked to death. That would definitely ruin your day. So this is sort of the core reasons of why we have AC power today, because we can transform it and ship it across long distances relatively cheaply. And the core aspect of a transformer is it can increase or decrease voltage, and also increase or decrease current, but in opposite direction. So a couple of key words here: primary winding, secondary winding. Primary winding is always the winding, that coil, that, wire coil wrapping around that transformer where you put your power in. And the secondary winding is where you take your power out. Very important terms. Now, the book talks about step up and step down. Those are important terms. The book also talks about a turns ratio. We're now on the bottom of page 226. So highlight those or underline those two sets of terms. The first one is step up or step down, and the second one is turns ratio. Okay. I also want to mention here that in showing you an example symbol for a transformer, they're actually giving you a classic transformer configuration, right? This is a classic transformer configuration. In a transformer, you always see these little ripples, these little bubbles. Somebody called them bubbles the other day. I thought that was kind of funny. They're like little ripples. They are an indication of a coil. And you'll see a set of bubbles around a line or a couple of lines. Now, if they're just two bubbles up against each other and no line in the middle, that means there's no chunk of steel in the middle of that transformer. Those are just two coils up against each other. A chunk of steel makes a better electromagnet in the middle. Therefore, a chunk of steel, iron core laminations, make for a better transformer. So typically on a transformer, you're going to see the primary coil labeled H1, 2, 3, and 4. You can set this up to have a variety of voltage inputs by depending on how you put jumpers between H2 and H3, where you attach your power connections. In this case, we're implying they get hooked to H1 and H4. And then on the secondary side, they're using the term X1 and X2. That is also a typical numbering scheme for the secondary on a power transformer. All right, so these are all very important little symbols that you guys should understand what they mean. And you'll see right again on page 227, they show you an example wiring diagram of how a transformer can work, and primary to secondary, primary to secondary. So the key with the transformer is if you have a primary winding, right, that's less turns than a secondary winding, we have more turns, then you get more voltage out of the secondary than you have coming into this primary. In this case, there's twice as many. So my ratio, the turns ratio, is 1 to 2. And that means my power remains constant. That's a trick question. Power always remains constant. You do lose a little bit through heat, resistance, but power remains constant. And what I do in this case, I'm going from a low voltage, 120 volts, to a much higher voltage, 240 volts, by having twice as many turns on the secondary. Step down goes in the opposite direction. So twice as many turns on the primary as the secondary. So it's a 2 to 1 transformer ratio. My voltage ratio is 2 to 1, which means it cuts it in half. My current ratio is doubled by cutting the voltage in half, by maintaining power consistent. That means my current needs to double. This is more typical of a control transformer. If I want 120 volts output, 120 volts AC is a pretty typical US control power that I would use for my switches and push buttons. So this is a more typical drawing for a control transformer. And I want to mention on the bottom of page 227, it highlights and emphasizes why we have less cost by using transformers to distribute power. An advantage of increasing voltage and reducing current is that power may be transmitted through smaller gauge wire, thus reducing the cost of power lines. So this is a very important point. I will point you to number 4 in the 11-1 checkpoint on the bottom of page 228. If the transformer of a turns ratio of 1 to 4, what is the transformer's power ratio? That is a trick question. The book loves to give you trick questions. Power ratio on any transformer, ignoring the efficiency loss, is always 1 to 1. All right, so let's go to 11.2. 11.2 starts talking about transformer connections, and then they bury this beautiful little drawing in here, which I think, if you're not familiar with residential and single phase commercial wiring, this is absolutely vital for you. Most businesses and almost all residences have this kind of wiring, and this, if you don't understand how it works, then you might find yourself making mistakes. And this is a really, really good diagram. It talks about the transformer that's on your power pole. That big transformer, that big can filled with oil, it's got 2 sets of coils. It's got what's called a step-down transformer, and don't ignore the proportion of those. Chances are your power is a lot higher than that, so you probably have more windings than they show physically. It's just meant to be a representation, not meant to show you the actual number of windings. But the key is on the output side. It's on the secondary side. Commercial and residentials tend at 240 volts tend to have 2 single phase hot wires. And if you use your voltmeter and put 1 lead on one side and 1 lead on the other, you should measure 240 volts AC. They do a center tap, and we're going to get into that term later on, in the middle of that transformer, and then they tie that center tap to ground. This is where they drive that giant giant copper rod down into the ground next to your building. And that giant copper rod is tied to the center tap, so that center tap then not only becomes the ground for your box, but we also use that same exact center tap, which is tied to the earth ground, as your common wire. So in your circuit box, that same wire is hooked up both to your green or bare copper ground wires, and it's also hooked up to all of your white wires, your common white wires in your single phase system. Some people don't realize that. And then you can take either one of your legs and use it with the white wire to create 120 volts. And you try to balance it, so you're not always using one leg or the other leg. So in your circuit breaker box, you try to distribute your load, so you're using a little from each leg of this transformer. So that's how single phase power works. And for your larger devices, like your electric dryers, your electric ovens, you would just use the 2 hot wires, the 240 volts. For your smaller devices, like your little toaster oven, or your electric hair dryer that you plug anywhere in the house, or your electric lights, you would just use one of the 2 legs plus the common wire. This is a very important drawing, and understanding it for single phase residential as well as commercial applications is critical. And they mention a few other important terms like overhead surface. I'm not going to highlight them because they're not really pertinent to this course, but they're very useful if you're going to be in the electrical world. So I'm going to pause this recording. All right, so also in this chapter, we mentioned taps. Taps are simply a way of connecting to the middle of a longer coil inside the transformer, and it's a way of getting different kind of voltages out of a transformer. For instance, a classic tapping arrangement is you might have a 480 volt input to a transformer, and then the output you might have the ability to get 240 volt if you attach to the ends of the coil, or you can get two separate 120 volt circuits like a single phase classic residential application. The most important purpose of us going through transformers in this course is, of course, talking about control transformers. Control transformers is used to step up and down or step down the voltage. Generally speaking, I might have three-phase power at, say, 208 or 480 or 460. And in that, when I hook up my giant machine, I don't want to have to run a whole different group of wires down to that machine. I just want to run three big fat, wires to bring down three-phase to that machine. And so inside the machine, I will use what's called a control transformer to convert that massive voltage coming out of that three-phase power down to a single phase 120, or single phase 120 down to a DC voltage to use as the control power, the low voltage power that I can run through my switches and my indicator lights and my coils and things like that. So that control stuff, that on off, that switch, those indicator lights, all that stuff needs a lower voltage. And according to our current electrical codes, and I can't remember the name of the code off the top of my head, that has to be 120 or lower AC. And in Europe, they're pretty much converting everything over to DC. So all control power has to be 24 volts DC in Europe. But here in the United States, we have a variety of both AC and DC. And they give you a few different examples of how you hook up a control transformer. And when you buy these transformers, they will give you a diagram to hook up. They'll say, all right, if you have 480 volt, then you may, hook up your 480 and you'll tie H4 to H2, and that'll be 480, and H3 to H1, and that'll be another 480 line, and so forth. So it'll give you different methods of hooking up those primary coils to allow either 480, 240, or whatever the input voltage is. And they go through a few different examples. And for instance, they give you the example of 240 volts and how you would hook that up. You would tie H4 and H3. And if you had 480, you would tie H3 and H2. And,
Rob, your camera disappeared.
All right. I am on page 231 if you're following along. Thanks for letting me know the camera disappeared. My camera seems to blink itself out for some reason every once in a while. I'm not sure why. Now, transformers, normally I would go through a whole selection process of transformers, but I don't think that that's critical. We do have a lovely lookup table. I will mention voltamps, VA. For some reason, we always talk about VA in terms of transformers, that instead of power like watts, we use voltamps, and that's the standard terminology. So you should always recognize that when they say VA, they mean voltamps, steady state voltamps. They're not sizing the transformer based on a brief input load. You always want to set it up based on steady state voltamps. And every transformer is going to be a little bit different. You always need to check your transformer specifications to be sure you understand what its ability is to handle loads. Also recognize that if your transformer is in a hotter environment, then you probably need to upsize it and you need to look at the specs of transformers. I will also mention that on page 233, this section on troubleshooting transformers is excellent. If you find that any one of these coils, if you disconnect your wires to it, right? You disconnect these wires, and if you find that you have that coil open, like there's no continuity at all, then you've got a problem with that transformer. That means that coil's burned out. You need to check all the coils separately when you're checking for continuity. Second thing is you might have a short. So if I put my continuity check, my ohm meter across one coil, and I get 0 or very, very low resistance, low ohms, then that means that something's shorted out. And what I should get is I should get the specified ohms across that coil. And if I put my my resistance meter across there, I should get the specified resistance across that coil. Each coil is going to have a specified resistance that you should be able to look up on a particular transformer. And so you're looking for open circuits, you're looking for short circuits, and you also want to make sure that none of the coils are shorted to the core. In other words, something burned out on your insulation or got nicked because somebody bumped it, and now your coil is just up against a steel core. If it's doing that, then it could cause a problem as well. So the troubleshooting talks about some basic methods to do that, and I'm going to demonstrate that briefly tomorrow.
I had a question.